So we have this whole telescope here, but you need to record the light. Back in the day, okay, yeah, there's clues. Back in the day, before the 1920s, let's say, you basically just had to look with your eye and draw a picture of whatever you saw. That's how astronomy was done. But in the 1920s, this new technology came about, and these are called photographic plates. Let's get a new page up here. So kind of the old school technology that began in the 1920s and lasted until about the 1970s, photographic plates. It's basically film, except on a piece of glass. And these are typically made by Kodak, big piece of glass, very thin, flexible, because often the plane, the focal plane where the image is created is not flat. It's sometimes curved a little bit. And so you're going to want your piece of film to be pressed into that curved focal plane. So you have to make it thin enough that you can press the glass into the plane where the image will be in focus. Otherwise, parts of your image will be out of focus. But it has to be strong enough that the glass won't break when you push it as well. These things are very delicate, and so I didn't bring one today instead of a picture of it. And it's all done in the negative. And so a dark spot on here is actually a detector of light. Again, it's a piece of glass with a coating across it, a photoemulsion. So when light comes in, it triggers a chemical reaction just like it does on film. You expose these things, as you saw with the 200-inch. Let me go back to that image. People used to ride up in the bucket up here, handling the photographic plates. You take the piece of glass, the astronomer holds it into the curved focal plane, exposes for as long as you need to, then you take it out, you hand it up to your assistant, who then runs to a dark room. And you keep it really dark so you don't have any unwanted exposure, and then you expose it like a piece of film. If you ever go over to Moorhead Observatory, like for office hours, as you're coming in the main doors, there's a room on the left that there's a sign with a light saying "in use." It's never lit up anymore, but that used to be a dark room for photographic plates. Again, the technology is 30, 40 years outdated, so we don't do it anymore, but the room's still there. I like store junk in it. And let's see here. Here you can see stars, you can see a galaxy right there. I brought one. Basically what they did is, using Schmidt telescopes, they imaged the whole sky on photographic plates, and then, well, in the modern day, those photographic plates have been scanned, and we can now access them all on computers. But back before that occurred, back before we had easy internet access, they made copies on plastic. And every major university in the country has a complete copy of the sky on plastic. And unfortunately, I don't think this is going to work. I don't think I have yeah, that doesn't work. You have to, well, we have over at Moorhead, we have light tables. You put it on the light table, you shine light through it, and you can see the stuff in the image. Maybe if I hold it. Can you see anything on there? Like, maybe not. Here, I'll just pass it around. So we have file upon file, you know, half a room full of these things. No one ever uses them anymore because they're all available online. But until our provost, Bruce Carney, retires, he won't let me get rid of it. So he's an astronomer. Then that's a nifty one. It's kind of a nebulosity. It's an extended region of gas and things. So I don't know if everyone will get to see it or not. Flashlight? No. Probably, no, you need really a big bench. I'm going to use the flashlight for something else. It won't be enough. Okay. Next, so this was kind of like from the 20s to the 70s. After that, we get into CCDs. These are called charge-coupled devices. So these are digital cameras. As I think I've explained before, they're similar to the digital cameras you have on your cell phones and laptops and all that, except ours are much more expensive because they're designed to work in very low light conditions. But they all kind of work like this. And all digital cameras have a CCD in them as the detector. So you have the CCD in there, but the electronics you build around it is what you call the camera. CCD is merely the detector. And so here's a CCD.
It doesn't look like much, but if you look at it under a microscope, you can see it's an array. You got a certain number of units this way and a certain number of units going the other way, so you have a grid. And these will correspond to pixels once the image is actually processed in your device or on your computer. Basically, as the light comes in, you can think each of those squares in the grid is a bucket that can hold charge. Most buckets hold water. These buckets hold charge, electrons. So the light comes in and it knocks off an electron that's sitting there, and it gets trapped in the bucket. As more light comes in, more light piles up. You can fill up these buckets, and the charge bleeds into other buckets. You've probably seen this if you take your digital camera and point it at the sun. You'll see bleed lines in the up and down directions. You might have noticed this in the lab too. If you get an exposure that's too long for the brightness of the object, it bleeds. That's just a charge overflowing its bucket and dumping into other buckets. But if you don't do it, then it's a matter of reading it out, and you read it out one row at a time. All the CCDs that you have with you today work the same way. This right here is electronics responsible for the reading, and measures the amount of charge in each of these buckets or pixels here, and reads it out. It's really good at two things: reading out the amount of charge without losing the charge. There's certain uncertainty in the reading process. Astronomers call that read noise, and it's something that goes into our measurement uncertainties. But the other thing it does really well is it moves charge from row to row. After you read out the top row, you move all the charge up one row without losing it. Otherwise, you'd have a lot of inaccuracy at the bottom of your image, because that charge has to get passed time and time and time and time again until it eventually has its turn to be read out. These are very good at passing charge along and pretty good at reading out charge up here at the top. Once you do it, it's all numerical. So you can take that grid and just write down the numbers. Here's a schematic of what two stars might look like if you zero in on them. This is a very small format. It's probably like 20 by 20. So just a piece of the digital camera readout. And you can see there are regions where you have more, and going around those regions you have less and less. Often to make it easier to look at, we'll color code it, grayscale usually. And so here's a numerical underlying information, but you can put a grayscale color scheme on top of that, and it looks like stars. One brighter and one fainter. And then we can do all sorts of measurements. We can count up the number of charges in certain apertures to measure the brightnesses of things compared to background noise. Now, one thing you probably noticed in here, this is a black and white image, and all astronomical cameras are black and white. Your cameras, for the most part, are color. So each pixel, each bucket that you saw in that grid before, or here even, in your cameras it's split into three: a red, a green, and a blue. And so as the light comes in, some of it goes into the red pixel, some goes into the green pixel, some goes into the blue pixel, and then the computer or your electronic device will combine those three. If there's a lot of red, it makes it a redder color. If it's an equal amount of all three, it's kind of a white color. But astronomers don't like that, because suppose you want to know how much blue light is where the red sensor was, and you can't recover that. So instead, we just have a black and white camera. We don't break our pixels up into specific colors, and if we want to see just a specific color, we put a filter in front of the camera. So if we want to make a color picture, we've got to take the picture 3 times. Once with the red filter, once with the green filter, and once with the blue filter. And each image will be black and white, but it'll be a black and white image of the red light, a black and white image of the green light, a black and white of the blue light, and we can combine it after the fact.
Here's just an example of color combination. This is in the first lab if you took it. So here's a color image. You see there are reds, there are greens, not very many blues, but there are whites, and white is a combination of all colors. So if you look up here, the red things are very bright. White in this image means there's a lot of red light from the red objects and also from the white objects. Here in the green, the brightest things tend to be the greener objects, and also again the white, which has green in it. Here the blue, there's not too much that's blue in this image, except it's on kind of a purplish sheet that has some blue in it, so that's kind of bright. And again, the white, which has blue in it. So we would take the image with the red, the green, the blue, and combine it into a color image on the computer. That's how we do it. Okay, here's a comparison of photographic film, or photographic plate, versus the CCD and color combination. So photographic plates, again, a plastic image of which you're passing around, they're about 2% efficient. The light that hits it, only 2% of it gets detected. The other 98% is lost. It didn't trigger the photographic emulsion. Now, CCDs, astronomical ones, tend to be anywhere from 60 to 90-some% efficient, depending on how much you're willing to pay. But let's say you pay for a good one, it's 95, 96% efficient. You can see in the same amount of time how much more light you're detecting than with the photographic film. When we switch the technology from the photographic plates to the CCDs, it's like our telescopes just got tremendously bigger. We're collecting much, much more light. It's the same as having a bigger mirror collecting more light. Except before we were wasting the light, now we're not wasting it, we're collecting pretty much all of it. And so here you can see the two bright stars, here you can see those stars and a whole bunch of other stars. And again, if you combine the red, the green, and the blue, you get a color image. So it would look like that. Questions?